Good morning. Our today's chapter is Rational and Irrational Numbers. Before moving to rational and irrational numbers, I am asking you a question. What are integers? Integers are the set 0, 1, 2, 3, etc. Then -1, -2, -3, etc. These are called integers. The second topic I am taking is rational numbers. A rational number is a ratio of two numbers, say 4 by 9, -3 by 10, 0 by -13. These all are rational numbers. But there is a condition that 4 by 9 means it is 4:9. That is why I called a ratio. The condition is that the numbers on the ratio should be integers. This is the first condition, and there is one more condition, that 0 should not be in the denominator. If I write, say, 5 by 0, this is not a rational number. 0 should not be in the denominator. So, a ratio of two integers, provided that the corresponding fraction should not have 0 in the denominator. Is 5 a rational number? Because I can write 5 as 5 divided by 1, so it is a rational number. The definition in your textbook is like this for rational numbers. Any number that can be expressed as a ratio of two integers. There they have written like this: any number that can be expressed as P by Q, where P and Q are integers and Q not equal to 0 is called a rational number. Is called rational number. And a rational number is always represented by the letter capital Q. So I have a question for you. My first question is 0.75 is a rational number? Is this a rational number? In the beginning, I asked one question whether 5 is a rational number. So explaining that, I wrote 5 as 5 by 1. So it is in the form of two integers, of ratio of two integers. So it is a rational number. The question is whether 0.75 is a rational number. So we need to check whether 0.75 can be expressed as a ratio of two integers. I can write 0.75 equal to 75 divided by 100. Both 75 and 100 are integers. Hence, 0.75 is a rational number. This I can further reduce to 3 by 4 by dividing the numerator and denominator by 25. This itself is a rational number. This is again a rational number, but it is in the simplified form. My second question to you is 12.135 is a rational number. .135 equal to 12.135 divided by, since there are 3 decimal points, I should here that decimal number is obtained by dividing 12,135 by 1000. So you will get 12.135. That means this number is again can be expressed as the ratio of two integers, provided that the denominator is not equal to 0. So this again is a rational number. Have you noticed these examples? Any similarity? This 0.75 and 12.135, these numbers are decimals, but there is a characteristic, there is a property in these two numbers. This comes under a category. The category is that this decimal terminates, that the digit does not continues infinitely. The digit does not continues. After 5 here, 0.75, after 5 there is no digit. The digit terminates there. So such decimals are called terminating decimal. And we found that a terminating decimal is a rational number. I will write this conclusion here. A terminating decimal is a rational number. Then what about a non-terminating decimal? That we need to check. So considering non-terminating decimals, my first question is 0.33, etc. That means etc. means the digit 3 is repeated infinitely. Is 0.0333 is a etc. is a rational number. You might have studied what I am going to say in your previous classes. So we need to check whether 0.333 etc. is a rational number. Let x is equal to 0.33 etc. This is equation number 1. Now multiply equation number 1 by 10. That means you need to multiply the left hand side and right hand side with 10. Multiplying left hand side with 10 will give 10x. Multiplying 0.33 by 10 means 1 3 will come before the decimal, and there will be again infinite number of 3's. If you take 1 3 from this side, there is no impact practically because the digits are infinite. Okay, this is equation number 2. Now 2 minus 1. 2 is 10x is equal to 3.333 etc. And equation number 1 is x is equal to 0.333 etc. Now subtracting. See, all these dots are 3 only. So I will get 0 only. On top it is 3, at the bottom there it is again 3. So all these are up to the decimal, I will get zeros only. And here 3 minus 0 is 3 equal to 10x minus x, 9x. So what we obtained is, subtracting these two equations, what we obtained is 9x is equal to 3. From this, x is equal to 3 by 9. X is 0.33. It is the same as 1 by 3, dividing by 3. X means 0.33 etc. That we expressed as 1 by 3. That means we were able to express this non-terminating, and there is one more peculiarity here, that this is recurring. Recurring have the meaning repeating, because you are not getting different digits here. The digits are repeated. So we found in this example that a non-terminating recurring decimal is a rational number. Let us see a few more examples. Is 1.2727 etc. is a rational number. Let x is equal to 1.2727 etc. Now I am going to multiply this equation 1 by 100. 100x is equal to 1. This 27 will come to the left side before the decimal. 127.2727, etc. Since two digits were repeated, that is why I multiplied with 100. In the earlier case, there was only one digit repeating. So, in order to make the digits after the decimals equal, I multiplied with 10. Now I got the same numbers in both the equations after the decimal. In both the equations, after the decimal, the digits are same. So if I make a subtraction, after decimal I will get only zeros. So that I will get an integer. Let us subtract 2 minus 1. 2 minus 1 means 100x minus x is 99x. It is 100x. 100x is equal to 127.2727, etc. And x is equal to 1.2727, etc. On subtracting all the digits from up to the decimal, because it's 7 by 7, 7 minus 7, 0, 2 minus 2, 0, 7 minus 7, 0, 2 minus 2, 0, that up to here, all digits will be zeros. And here, before this decimal, 127 minus 1 is 126. And here, 100x minus x is 99x. If you add an x to 99x, you will get 100x. So we got 99x is equal to 126. 126.000 means 126 only, is 126. So x is equal to 126 divided by 99. This can be divided by 9. So it will become 11 and 14. So here again we obtained that this is again a non-terminating recurring even though one is not repeating, this decimal is again considered as a non-terminating recurring decimal. So in this example also we obtained that it is a rational number. So let me write it, that conclusion here. And non-terminating recurring decimal is also a rational number. Let us consider one more example, a little bit different type of number, so that we can be sure about this conclusion. The third question is 3.5721 etc. is a rational number. This again comes under this decimal number again comes under the category non-terminating, because here there is dot dot, so it is non-terminating, and again it is repeating. Even though this 3 and 5 are not repeating, 721 is repeating, infinitely. So it is again a non-terminating recurring decimal. Let x is equal to 3.5721721, etc. Now I am going to find 10x will be equal to 35.721721, etc. This 5 will come before the decimal. Now I need see in these equations the digits after the decimals are not the same. Here it is 5 and here it is 7. So this equation, say this is equation number 2, this is equation number 1. For 2, I am again multiplying by 1000. Multiplying equation number 2 by 1000. 1000 into 10x. 10,000x. 1000 into this. Why I multiplied with 1000 is that here 3 digits were repeating. So I will get 35. This 721 will also come before the decimal. 35721. Then after 721, 721, etc. These two equations, see, after decimal, the digits are same. 721, 721, here again 721, 721. And if I make a subtraction, then I will get after decimal, all digits are zeros. So 3 minus 2. 3 is 10,000 x equal to 35721.721, etc. And the other one is 10x equal to 35.721, etc. If I do a subtraction here, after this decimal, all the digits are same, 7, 2, 1, 7, 2. So all are zeros. 35721 minus 35. That will be obtained as 5 and this is 6. This is 8. 5, 3. So eventually I got an integer. And what about this 10,000x minus 10x? That is 9,990x. So the equation I got is 9,990x equal to 35686. Therefore, x is equal to 35686 divided by 9,990. On simplification of this will give 17843 divided by 4995 dividing by 2. So in the third example also we obtained it as a rational number. So this is, we can conclude that a non-terminating recurring decimal is also a rational number. Is there any other possibility? There is possibility non-terminating. Here it is recurring. There can be non-recurring. Means the digits here will not be repeating. You will get different digits. If any such numbers are there? Such numbers are there. If you go for finding the square root of 2, you will get a number 1.414 2135 62 37309, and if you go on continue, that you will find that it continues infinitely, and there is no definite pattern. There is no numbers or a collection of numbers are repeating. Numbers are never repeated. It comes random. This number can be categorized as non-terminating. This is non-terminating, non-terminating, and non-recurring. Non-recurring. Root 3 also is such a number. If you are going to find square root of root 3, you will get 1.732 050 8076, etc. And root 5 is also such a number. Root 5 is equal to 2.236 06 79775, etc. So these all numbers are non-terminating and non-recurring. Is these numbers are rational? Since after the decimal, nowhere else the digits are repeating, we can make the digits after the decimal 0 and getting an integer only if the digits are repeated at somewhere. At some places, the digits should repeat. If it is not repeating, then we won't be able to get an integer there. So by this method, we cannot convert these decimals into rational numbers. And in the first method also, that was terminating decimal. Since the digits are not terminating, suppose if it is 1.4414, if it was only this much, then we should have wrote it like this: 1414 divided by 1000. Since the digits are not repeating, how many zeros you will put? The digits are not repeating. So by those two methods, we are unable to convert these decimals into rational numbers. And till date, there is no method available to convert these into rational numbers. Since this cannot be converted into a rational number, these are called irrational numbers. Irrational numbers. So our third conclusion is that a non-terminating, non-recurring decimal is an irrational number. In the next class, we will prove root 2, root 3 and root 5 are irrational number. Thank you.